to the restroom, falling asleep. I've taught for a long time. It's important to take cat naps and to stretch legs. There's no, especially for the junior scientists in the room, there's no judgment. Please do what you need to do as long as you're not disturbing your neighbor. So one of the primary ways that astronomers learn about the universe is by making maps. And these maps don't just show us what things are where in the universe. They include things like where objects are, how far away they are from us, what colors the objects are, maybe how quickly they're moving towards us and away from us, or from side to side across the sky. And by combining these different dimensions of ways in which we can map the universe, astronomers can evolve our physical understanding of how did the universe come to be? What is our physical place in the universe? What's happened over the last 13 billion years to get us here? And by pursuing the answers to questions like these with physics, over the course of human history, we've also philosophically evolved our understanding of our place in the universe. So my focus tonight in this talk is to highlight ways that mapping the Milky Way itself, our own cosmic backyard, has evolved our understanding of our place in the universe, both physically and philosophically. Now, we're going to start looking at this. Let's see. Yeah, that works well. This image here, which was taken by an amateur astronomer. So how many folks have looked with your naked eye up at the night sky and seen this Milky Way? Right? And so the origin of the phrase Milky Way to refer to the galaxy that we live in itself is quite literally what this sky looks like. And every single star that we see in this picture, every single blip of light, every single star your eye sees when you look up at the sky belongs to our Milky Way galaxy. They happen to be some of the nearest stars and some of the most intrinsically luminous stars that we can see. And this milky structure that our eyes mapped from early on is sort of modeled in appearance, and this is gas and dust that's contained within a disk. And we actually live within that gas and dust disk, as I'll show you again in a few slides. So it's only been less than 100 years that the Milky Way hasn't meant the entire universe to humans. It's actually only been a few hundred years that the solar system itself wasn't the whole universe to humans. And in fact, in 1609, just after the invention of the telescope, Galileo made some amazing discoveries by pointing one of those first spyglasses up at the sky and presented these observations in a paper, in a writing called The Starry Messenger. One of the things he did was he discovered the moons of Jupiter, and so here's an image from that writing which shows his discovery of moons of Jupiter, which is really quite amazing. And he published that very, very quickly before he quite figured out everything about them. A second thing that Galileo did was to point that spyglass towards that milky region of the sky and made the observation, for the galaxy is nothing else than a congeries of innumerable stars distributed in clusters. And so with that telescope, he was able to see, as you look across the sky closer and closer to that Milky Band, you see more and more stars. And that was the first real sense that there was an increasing number of stars in this disk-like shape around where we lived on Earth. So fast forward about 150 years, another very well-known step in the history of mapping the Milky Way was done in the late 18th century by Caroline and William Herschel, who worked together, again, just using their eyes looking through a telescope and recording and drawing what they saw, by assuming that all stars they could observe through this 48-inch telescope had the same intrinsic brightness, like they were all light bulbs emitting the same exact amount of watts. They sketched out what they thought was the relative shape and distances to these stars. Now, when I look at this map, and I've looked at it many times as a student and also as a teacher, it doesn't look that impressive. I mean, it was done in the 18th century, but you just sort of see this blob of stars. It's pretty cool that the rough, flattened shape of the Milky Way comes across in here. But before we dismiss the majesty of this figure, I want to give everyone a sense of how far apart are those stars? Right? How far apart are they actually? What's a sense of scale? So the scale model that we're going to think about is such that the size of roughly one of our heads is the actual size of the sun. Okay? And we're going to put that sun here in Bremerton in this theater. And so you can see that we've got Taylor Swift's head there at the seeFilm Theater. And so the distance between the sun and Earth would maybe be about 70 feet. So let's say, I'm not a really good judge of distance, way the back of the room from where my head is. Oh, hey, Michael. And the size of a peppercorn, okay? That would be the rough scale. What about the outer reaches of the solar system? Don't shout out the answers. Think about, where might Neptune be if Neptune was the size of a cotton ball? And so the solar system out to Neptune would roughly fill the area between right here where the theater is and out to where the ferry dock is. And I've drawn this circle in to give a rough sense of where Neptune might be. Neptune's actually on an elliptical, not a circular orbit, like all of the planets, but it gives us a rough sense of scale. Okay, so this is how much space the solar system takes up. Think to yourself, where's the next star? How far away is the next star as the size of the human head in this scale? And just take a moment and then I'll show on the next slide. Do any of our junior scientists, future scientists in the room, want to say what they think? Okay, up front, what's your name?
Jebediah.
Hi, Jebediah. What do you think?
If the edge of the solar system would be the edge of the Oort cloud, you'd be 1/3 of the way there.
Jebediah? Can you hear me now? We have a very educated junior scientist sitting in the front row. I love it. I was telling people earlier when I've done public outreach, the children that come to the talks know so much astronomy. It's amazing. So I cheated a little bit. When I said the edge of the solar system, I meant where Neptune is. So the Oort cloud is much farther out than that, but you are very right. Can you talk very loudly, junior scientist in the yellow headband? Leona, what do you think? How far away do you think the next star might be? New York City. That's a bold guess, Leona. So let's see where our next Taylor Swift head appears on the next slide. Leona is right. And if this was The Price is Right, you would win the Showcase Showdown. But it's not, and I actually was going to bring stuff to give away, but I have nothing. Except for the fact that you are clearly a future scientist. Okay, great. So at this point, when I talk to folks, I often ask you to reflect just a little bit, again, philosophically on, wow, space is really empty. What do you think of that? Does this affect how you feel about the nearest stars or any of these astronomical endeavors? And when I work with students and I have them break up into small groups to think and share together, sometimes they come back rather dejected, saying, oh, we are so insignificant. But after thinking about this over the years as an astronomer, I actually have a much more Stephen Colbert-like interpretation of this, which is, wow, we humans here on Earth have been able to figure out how to study physics on Earth, to learn enough about how the laws of physics works, to look out there and learn about how the universe operates at these enormous distances that we'll never be able to travel to ourselves. It is simultaneously humbling and inspiring to me about what humankind can accomplish. It is very exciting. And so this puts that humble picture that we saw a couple slides ago into a new perspective when we appreciate some of these distances. And I'm going to go ahead and skip over 200 more years of astronomical history to the picture we had around the turn of the century of the Milky Way and what its contents are. And this more modern picture we were able to figure out by a series of large surveys taken of the sky in the 20th century, largely based on photographic plates and observations of stars observed in photographic plates. And so by the turn of the century, we had a sense of galaxies like the Milky Way had hundreds of billions of stars, and there are hundreds of billions of galaxies within the universe itself, an enormous number. And when I think of this, there's a quote, a really poignant quote by Arthur C. Clarke that always comes to mind, which is that two possibilities exist. One is that we're alone in the universe, and one is that we are not. Either way is terrifying, which is absolutely the case to me when I think about this. It sends a little bit of shivers up my arms when I think about it. Okay, so back to the Milky Way from here on out. So here's a picture of a galaxy. It's not the Milky Way because we're inside the Milky Way, but I pulled a couple of pictures up of other galaxies that we can see from the outside that we think look a little something like the Milky Way does. So this might be a little bit reminiscent of that first image we saw. We see there's some glowing light, but there's this black line here that's obscuring our view of the starlight distributed in this disk. And that is gas and dust in the disk of this galaxy. And so we now understand that we live about 2/3 of the way out in a disk like this. Some of you may have seen those t-shirts. You are here. That is true. And I again refer to this. It can sometimes be hard to visualize how we can live inside of a disk and still view our sky like this. I like to cook and eat a lot, so I'll often think about, well, what if I lived inside a hamburger patty, or what if I lived inside a pizza or a cookie? What would it look like as I was sitting inside the chocolate chip cookie, looking towards the center, and then up and away, and then down underneath the cookie? Well, if I was looking straight through the center of the cookie, I'd see a bunch of chocolate chips, but as I was looking up and up and up and up, I was looking straight up through the cookie, there may not really be so many chocolate chips between me and the sky in that line of sight. And so here we have that disk that we're looking at, even though we're actually embedded within it. A rough size of this disk of the Milky Way and galaxies like it is 75,000 light years. And that's a unit of distance measurement that's really different than what we use every day. And the reason that we use such different units of measurement is because these distances are so enormous, you kind of lose track of what it means to say how big things are in feet or in miles. And so this distance means how far light travels in 75,000 years. So even if we look at the nearest star to us, we're looking a few years into the past. Looking all the way across our own galaxy even, we are looking tens of thousands of years into the past, because that's how long it took light to travel from there to here. So in addition to the stars in our galaxy and the gas and dust that we see in our galaxy that can obscure our view of parts of the sky, around the turn of the century, we knew of hundreds of clusters of stars that are in our galaxy and orbiting around it as well. And I just showed two examples here. Here's a loose cluster of stars. They formed relatively recently. You can see each star, there's some fuzzy diffuseness there because of the gas and dust nearby those. And here's a very dense cluster of stars. We can see some of the individual stars in the outskirts, but there's so many stars together here that they become unresolved into a smooth blob of light. And clusters like these orbit around the center of a Milky Way in a disk, but some of them also orbit around the galaxy itself on randomly oriented trajectories. So if I turn that edge-on galaxy that I showed you a few slides ago by 90 degrees, it looks a little something like this. It looks like a spiral, we have set of spirals. We think the Milky Way has a bar-like shape in its center as well. So the Milky Way is a spiral galaxy with forming stars out of the gas and dust in that disk. Now, any of you that have ever looked at a picture of a galaxy, maybe some of you have looked at a lot and some of you haven't looked at so many, whether it's in a talk like this, on the computer, in a magazine, they look a little something like this. Sometimes they have funnier shapes. But interestingly, even though this part of the galaxy that we see with our eyes contains, 98% of the light in a galaxy, the vast majority of a galaxy's volume is located very far away from that center. That's less than 1/1000th, maybe 100,000th of the actual volume of the galaxy. And so the part of galaxies that I'm most interested in aren't in that bright part that we can see with our eyes in pictures. It's in this extended, diffuse and ghostly halo within which we believe all galaxies are embedded. And there's both observational and theoretical evidence for that. And so by the turn of the century, we just started to get an observational and theoretical taste for what these enormous ghostly halos should show us observationally and what they could reveal to us about the overall nature of galaxies. So in the year 2000, we had observational and theoretical reason to believe there is an enormous halo of dark matter, and I'm going to tell you exactly what dark matter is on the next slide. There were 11 galaxies known to be orbiting around the Milky Way itself, represented by these teensy little smudges here, which I photoshopped in. If you've ever heard of the Magellanic Clouds, those are our two brightest dwarf galaxy companions. You can see them with your naked eye from the southern hemisphere, but they're far more luminous than the other 9. And we knew of one cannibalized dwarf galaxy, the Sagittarius dwarf, whose stars were spewed all around the sky, encircling the Milky Way as evidence for a galaxy that once was whole and was slowly getting accumulated and eaten up by the Milky Way. So this one stream of stars. And a great thing about this burgeoning picture around the year 2000, first I have to tell you what dark matter is. Before I get ahead of myself, dark matter, this is not dark matter because we can see it by its electromagnetic radiation. This is dark matter because we cannot see it by its electromagnetic radiation. We can infer the presence of this matter by the gravitational effect it has on other things, and that is all we need to know about dark matter for purposes of the present discussion. And actually, I don't know much more about dark matter than that myself. It's something that I have in common with all astronomers and particle physicists who are all very, very interested to figure out what dark matter is. But the amazingly cool thing is, I should never say the amazingly cool thing is, an amazingly cool thing is, if we do a computer simulation of the universe and say, well, what if I know that there's a whole bunch of dark matter? What if I know that it obeys Newton's laws of gravity, and I press go and see what Newton's laws of gravity does to this matter? Where would the matter be at the present day when we exist to observe the universe? And astronomers do this even though we don't know exactly what the dark matter is, and we predict a distribution of galaxies and mass that matches our observed distribution extraordinarily well. So we're not just making things up as we go along. There's a lot of reasons to believe that there's this dark matter in the universe, and in a universe with lots of dark matter, we shouldn't just have these disks of galaxies. They should be embedded in these enormous ghostly halos of stars. And this image made from one simulation of how the Milky Way may have formed, with our eyes looking right now at the screen, we see there's obviously a ghostly halo of stars that extend a very, very far distance. This is about 1.5 million light years across in this image. But of course, this image was made so we could see it with our eyes. It's very, very hard to observe these stars. But that one stream of Sagittarius in the year 2000 gave us some idea that there might be something to this model. Okay, well, what does this model tell us about where matter should be? Maybe it's not just stars there, maybe there should be dark matter itself around the Milky Way galaxy, which may or may not have stars associated with it. Well, this is one picture of one realization of how the Milky Way may have formed. And again, we have our happy little disk galaxy here in the center, if I can evoke some Bob Ross. And far outside of this disk of the galaxy, our eyes can pick up many different bright blips of light. There are in fact thousands of them in this image. The simulation is more recent than the turn of the century, but forgive me, I think it's a very nice illustration. Each one of those is a clump of dark matter that's predicted to be orbiting the Milky Way. It's just one realization of clumps of dark matter to be orbiting the Milky Way. Thousands are predicted, and at the turn of the century, we observed 11 of them to be lit up by these dwarf galaxies. And I already mentioned that the Magellanic Clouds were 2 of them. More typical examples of dwarf galaxies look something a little like this. This is the Leo 2 galaxy, and we can see with our eyes here sets of stars. We can see with our eyes some are redder and some are a little bit bluer than others. As of the turn of the century, this was the least luminous galaxy known in the universe, the Draco galaxy. Draco, Leo 2, and all the other dwarfs orbiting the Milky Way are named after the constellations they're in. And this galaxy is harder to see. But what you can do is think with your eyes, look with your eyes. About how many stars per area do I see here? But if I look at the edge of this image, about how many stars per area are there? There are fewer stars that my eye picks up on the edge than in the center. That's our eye showing us where the galaxy is. And that's your eye doing exactly what computer algorithms have done since the turn of the century to discover a large number more galaxies that are effectively invisible in images like this, which is what I'll turn to now. So the turn of the century, we have this paradigm. There should be lots of dark matter around our galaxy. There should be this big ghostly halo. We have hints. We see these 11 dwarf galaxies orbiting the Milky Way. We see one stream of stars around the Milky Way. And digital survey astronomy unexpectedly, again, revolutionized this picture of the Milky Way after the turn of the century. The Sloan Digital Sky Survey, this is a picture of the telescope. It's in New Mexico near Alamogordo. A student of mine at Haverford College took this cool picture, setting his shutter open for a while. You can see the star trails. The Sloan Digital Sky Survey was, you could think of it like a precursor to LSST. It's a similar concept without the time component, as I'll wrap up at the end with. DSS observed a huge fraction of the sky, about a third of the sky. It took pictures of the sky in many different colors, so we didn't just see the brightnesses of stars, but we saw what colors they were. And this enabled us to make many new discoveries of galaxies and cannibalized streams of stars. The Dark Energy Survey is a new and ongoing survey taking place in the southern hemisphere that's imaging 1/8 of the sky in a similar way. And even just over the last week, I think it was last night at dinner, I checked Twitter and saw that this survey had found 8 more galaxies around the Milky Way that are effectively invisible in pictures of the sky. Okay, so how can we do this? What is it about seeing both the brightnesses and the colors of stars that unexpectedly revolutionized what we see around the Milky Way? And then that will lead into the final bit of the talk, which is, well, then how will LSST do so again? So the example that I'm going to show you here is from the Space Telescope Science Institute, and it's illustrated with an image of a star cluster taken with the Hubble Space Telescope. But the basic principle is the same as we can observe here down on Earth. When you look at a picture of the sky, you can see some stars are bluer and redder and in between. And even when you look up at the night sky, you know, Betelgeuse in the Orion constellation is a really nice example. It's one of the reddest looking stars in the sky. And astronomers can organize stars. You can think of it in your mind, how many stars are blue and red. Or you can actually make a plot, make a figure, organizing the stars red to blue and bright to faint. And so we can sort it so the bluer stars are on the left and the redder stars are on the right. And you see that there's different numbers of stars of different colors. And now we can sort this again and put the fainter stars on the bottom and the brighter stars on the top. And what we see is stars don't just have random combinations of colors and brightnesses. Actually, the basic laws of physics tell us that given the way stars burn, there are certain sets of colors and brightnesses that they have, both when they're born and then over the courses of their lifetimes. Where the color of a star primarily reflects the surface temperature of that star, with the blue stars being the hottest and the red stars being the coolest. Now, I'm going to put up names of some types of stars on this diagram because I'll briefly refer to them in the next few slides. So the vast majority of stars in the universe are on the main sequence, which is why it's called the main sequence. When a star is born, it's somewhere along this line. It's either cool and dim or warmer and more luminous. M giants are a type of giant star. By the word giant, it quite literally means giant, physically enormous. And the turnoff refers to the stars that are the bluest and hottest stars that exist within a galaxy or a star cluster. And astronomers armed with this knowledge can not just look at pictures of the sky with our eyes, but we can analyze lists of millions and millions of numbers of the colors and of the brightnesses of these stars to try to pick out different populations, to map what they look like, to map where they are, to look for evidence that they're distributed in lines across the sky or moving together in new galaxies that you would never see if you just looked at a picture of the sky. And so using this approach, data such as that observed in the Sloan Digital Sky Survey and now the Dark Energy Survey has led to the discovery of 35 new, nearly invisible galaxies orbiting our own in the last 10 years? Is it 11 years now? Time goes by so quickly. In the last 10 or 11 years. Right, so when I was in graduate school, we didn't have any idea that galaxies like this could exist. These invisible galaxies, I'll show you one on the next slide. 35 is triple the number of galaxy neighbors that we knew about when I was in graduate school. It took us an entire human history to find those first 11. The Magellanic Clouds with their eyes on the sky, and the others with eyes on photographs of the sky. We've more than quadrupled it, and we think that there are hundreds more yet to be discovered. So one of the first two galaxies to be discovered is the Ursa Major Dwarf. And it is 1/1,000,000th the star content of the Milky Way, 1/1,000,000th the luminosity of the Milky Way. And it's in a picture of the sky here. Now, I can't see it, and I know where to look. But there's a reason these galaxies weren't yet found before. The other galaxy that was found around the same time, which I tend to avoid putting in talks, yet it seems too self-congratulatory, is the Willman 1 galaxy, which is only 1/10,000,000th of the Milky Way's luminosity that was discovered with the Sloan Digital Sky Survey data. And at the time, these two were found around the same time during my first postdoc. And we expected to find things that were less luminous than those that had been found before, but we didn't expect there to be an enormous gap of a factor of 50,000 between Draco, that one that we could hardly see in the picture, and the next galaxies to be found. So how the heck do astronomers see that it's there? How do we use the survey data to even have a hint to look at something interesting? So we analyze the colors and the brightnesses of stars. Our statistical analysis tells us there might be something interesting there. Take a closer look. And then we separate stars by their colors and their brightnesses, and we look to see if we see that well-defined pattern that I showed you in that animation from the Hubble Space Telescope. And these are in astronomer units. I forgot to take the one that has blue written over here and red written over here, just like in the animation, and faint written down here and bright written up here, just like in the animation. And it takes a bit of an acquired taste and experience to see the screamingly obvious now to me distribution of stars here along a very well-defined sequence in this image. But this is the sort of thing that we can use our survey data to look at and say, I think the galaxy is there, and I think it's about this far away, and I think it's about this old. And then we can get more data to look at how fast it's moving, and if those stars are moving together. And that's the full set of fingerprinting that we do on these types of objects to learn what makes them tick. What these possible building blocks of all larger galaxies, how do they get to be the way they are? Another major revolution in our understanding of the Milky Way that has come from these digital surveys is pioneered in large part by somebody sitting in the second row here, Carl Gromer, is finding the fact that we don't just have one galaxy that's been cannibalized by the Milky Way. There's an enormous number of streams of stars around the Milky Way galaxy. So this is an iconic figure to astronomer named Field of Streams. So Google Field of Streams, and you will get this by Vasily Belokrov and collaborators. And we see that there's regions of brighter and darker in this figure. The brighter regions show you areas where there's more of those main sequence stars. The darker are regions where there's fewer main sequence stars. So the brighter areas show you where stars are concentrated, where they're congregated on the sky. So this bright swath here is where that stream that's been known about for a while is. This little one down here, that's a star cluster in the middle, and it has a really skinny little stream that's been mapped to extend over a number of degrees of sky. This blobby density here is a cloud of stars. You see, again, the pattern. Everything is named after the constellation they're in. The Orphan stream, which is tough to pick up with our eye in this figure, and the Monoceros ring is another overdensity found. the Virgo overdensity. And there's many, many more tiny little thin streams and thick streams that have been found over the sky. Thanks to this work. And actually, I wanted to say this before. I keep saying this is what we've learned about the Milky Way. The Milky Way is right now the only galaxy that's, well, close enough, we're in it, such that we can observe the sky with this much detail and observe sets of individual stars with this much detail. So we're actually not just learning about the Milky Way. The Milky Way is the lens through which we learn about all other galaxies in the universe. So this is also helping us understand how to interpret our observations of other galaxies. And the final thing that I'll highlight, also in a self-congratulatory way, as a cool discovery that's come out of the current generation of digital sky surveys, is that we've started to find and confirm individual stars that are at the very, very outermost reaches of the Milky Way galaxy, at the very, very edge or beyond of where theory predicts we should be seeing stars in this ghostly halo. And so work led by my colleague John Bochansky led to the discovery of two of these bright and giant stars. I just put two big red circles here. No, the best I could do. Oh, and I lost the galaxy. There is oh, here's the galaxy. Over 700,000 light years from the sun. But they're bound to our own Milky Way. We think they are. Okay. So, the last thing that I'll talk about is how the LSST will again revolutionize this picture of the Milky Way. So I'm just starting as deputy director of the project. I just moved to Tucson, but I've been involved with LSST for about 7.5 years to 8 years already. I was one of the first dissertations to be done with Sloan Digital Sky Survey data, that work that led to the discovery of those first two invisible galaxies, now followed up by several dozen. And so I was very interested in a long time in survey astronomy and what it could do around the Milky Way. And there's a few different special things that LSST is going to do for our knowledge. And for those of you that were here earlier, Bob gave a bit of an overview of some of the basics of the LSST telescope. It's got about a 6-meter effective size, light gathering bucket size. You can imagine a telescope is quite literally a bucket that gathers light like a regular bucket could gather raindrops. 3 billion pixels in its camera gives it an enormous light gathering power. And not only do we get to see a bunch of the sky at once and observe very efficiently, but because LSST will observe the sky in the southern hemisphere many times over, hundreds of times over its 10-year lifetime of the project, we'll get a movie-like window into the universe, not just a very deep and wide window into the universe. So for the Milky Way, this translates into opening up 1,000 times the volume for studying the Milky Way with stars. So all of those discoveries I just showed you, we'll be able to make discoveries like that over 1,000 times the volume with LSST. With this movie-like window onto the Milky Way, we'll learn about the motions of stars in the Milky Way's disk and its ghostly halo. And from that, it will contribute to our understanding of the mass of the Milky Way and of the history of how stars got to where they are. We can rewind that movie and figure out, where did these streams of stars come from? What did they start out like? And then the third thing, but certainly not the least important thing, is that for us in the United States, this data will be for everyone. Every US astronomer, no matter what institution you're at, if you're me, we'll all get the data in the same form at the same time. Everyone in this room will have avenues to access the data. Just one of the many things on the planning phases in the Education and Public Outreach Program is something called LSST at Home. You might have heard of SETI at Home. There are ways to get involved with different astronomical projects at home already. And LSST is going to become a really big player in this very early on. So definitely keep an eye out for LSST, especially if you're an educator, K through 12 and beyond. My hope, and the hope of many others, is that the LSST is going to revolutionize the way hands-on and research-like inquiry can come into the classroom from very early times. So just to give you a couple of highlights about how this is going to be done, I showed you how Sloan Digital Sky Survey revolutionized our understanding of the Milky Way, and here's a couple snapshots of SDSS data from a paper led by project scientist Jelko Ivezic. And we don't have LSST images yet, but here's two comparison images of the sorts of ways that this patch of sky would look if LSST observations instead of SDSS. And this is similar to just a single LSST snapshot. And this comparison highlights what adding up all those snapshots together might reveal. And so our eye shows us the enormous amount of sources and shapes that we'll be able to see with LSST that we haven't seen with SDSS. And this is going to be big data. So you should remember all of these numbers. I know there's some people in here that are really happy with this slide. So we're going to think of them now. I really like this slide. So 15 terabytes of data per day. You know, think about how much music you have or how many movies you have. How big is your hard drive at home that you're sharing with your family? There'll be about 37 billion objects in the final catalog, 20 billion galaxies, 17 billion stars. There'll be 30 trillion forced photometry measurements, which means that at the end of the survey, we'll stack up all the observations together and see where every single observation is, and then go back to all of the single pictures and ask, oh, well, what did that part of the sky look like then, and then, even if we didn't necessarily see that object in every picture. A huge number of variable sources will be found. A big aspect of LSST that I think Lynn Jones talked about a bit last night, that Luciane is going to be talking about on Thursday, are the changing universe, the dynamically changing universe. What are we going to learn about that goes boom from night to night? And those images are going to be turned into enormous lists of numbers that are going to be released to the public and to scientists 11 times over the course of this 10-year survey. And so all we really need to remember about this slide is that this is what the data stream is going to look like. And we're going to need a few of these to keep all of the data. And so just a couple last images, again, to hammer it home even more. 1,000 times more volume around the Milky Way will be accessible with LSST. This is another nice image from Željko Vezic's overview paper in collaboration with many LSSTers. This cool little color image shows a density map of Milky Way stars observed in the Sun Digital Sky Survey. And this entire area shows the volume within which we'll be able to conduct similar fidelity observations with LSST. And so the sorts of things I'm hoping will come out of these data after survey operations begin just 7 years from now. So 7 plus 10, 17. I don't think I'll be retired by the time the survey is over. I hope not. My kid will certainly be in college and graduated from college. The true number of these invisible galaxies around the Milky Way and beyond. Right, in SDSS, we found this type of galaxy that we're pretty sure is the most numerous type of galaxy in the universe right now. But we're not confident of it yet. We don't know exactly how they form and how they influence the very first structure formation in the universe. I think LSST will be the survey to answer that question. We may find possibly previously unseen types of galaxies. You can ask me, what do I mean by that? And I could maybe make up an answer, but I don't know. We didn't think that we'd see possibly or previously unseen types of galaxies in the Sun Digital Sky Survey data flow. So it's the expected, unexpected. There's so many different types of things you might discover. Known knowns, unknown unknowns, known unknowns. That's a known unknown, I think. The Milky Way's full set of ghostly star streams as evidence of galaxies that used to exist but have since been gobbled up by the Milky Way. And streams like these, and folks like Carl Grömer are sitting here, we will disentangle and try to decode what these streams are, what they mean for the formation of our Milky Way, and again, using the Milky Way as the lens for other galaxies. And then to fully map out the edge of the Milky Way stellar halo. So, just two fun pictures. I'll relieve you of science. The construction of LSST formally started last summer, and there was a first stone-laying ceremony in Chile on Cerro Pachón back in April to celebrate the start of construction. And so this is one image here taken where we see Michelle Bachelet, the president of Chile, Franz Cordova, the director of the National Science Foundation, and Steve Kahn, who is the director of the LSST here, celebrating at the end of this lovely, lovely ceremony right at the construction site. It was like a movie set. We were in this really cool tent, and you can see behind them there was this window built into the tent, and you were looking out on all of the rocks. It was really fun. A number of folks in the room here were there, including me, and I was very excited by the whole thing, and I hope that you are too. So I'll take any questions. Thank you.
Actually, I probably don't need that, Bob. No, you don't.
No, you don't.
Doctor, the two questions. First, 15 terabytes of data a day, to me, is overwhelming. And how do we expect to process that amount of data over a long period of time?
That's her job.
Lots and lots of computers.
Rossi. And Rossi's going to be giving a talk at the planetarium on Friday. I'll turn it over to you.
Not exactly about this, but yes, so I'm part of the LSST data management group, which is a huge part of the LSST effort to develop the software and capabilities of actually processing this data. It is challenging, and when you edit something with Photoshop and get it wrong, you go back and do it again, and that doesn't take so long. If you have 5 petabytes a year and you make a mistake, you really don't want to go back and redo it all over again. So we're putting a lot of effort in trying to get this right first time, which would be novel for astronomical software, but we're going to do our best.
And a follow-on, Doctor, you mentioned you hope to find or expect to find many more invisible galaxies. Is that part of the answer for the extra mass in the universe we think is causing the dark matter problem with the extra gravity?
So that's an excellent question. The question is, would finding these extra galaxies go to solve any of the missing mass problem? So there's a few different observational challenges with our dark matter paradigm.
That have been highlighted over the last decade, especially around the year, starting in the late 90s in particular. And wondering the location of the matter isn't how, is a problem that's been talked about a lot. Where is the dark matter and where are the missing, protons, neutrons, and electrons of the universe are two different things that people talk about. So the galaxies that we're looking for are going to go a long way to answering where is the dark matter. One way to phrase that are, where are the missing galaxies? So the theorists, of course, have said, where are the missing galaxies? And as an observer, I'd say, well, why are you predicting all this extra dark matter? And so a combination of our observations revealing to us, wow, there's actually probably hundreds of clumps of dark matter lit up by galaxies, and a better understanding of the conditions under which stars form are going to go a long way, if not all the way, towards answering that question. That's exactly right. Oh, we have a question up here in the front.
I was wondering about the shape you mentioned of the disc-type shape of the Milky Way and then another formation. I hope you didn't already answer this. How do they come to be in a disc shape? It looks like it's a whirlwind or some type of effect.
Great. So the question is about how do galaxies form and why do different galaxies have different types of shapes? And so it depends on how galaxies form themselves. So gas can cool, and when gas cools via interacting with itself, it condenses. The density of it increases. Okay? And so when the density of gas increases, it was moving with any angular momentum for any rotation, it will speed up as it condenses. Sort of like the figure skater speeds up when he or she brings her arms in. And my crude Astro 101 level answer to what happens from there is, what if you take a ball of pizza dough and you spin it up and it flattens out? And so that's one very cartoonish way of how galaxies form. But there are different ways to form. To really get something flattened in a disk, you need to have enough gravity to hold itself in, which is different than the physics of the pizza dough, which is why it's a little bit of a dirty analogy. But when you condense, you tend to spin faster. And if something has enough gravity, then it also condenses in the direction that is perpendicular to the spin. Great.
Pardon me?
Yeah, I do.
Other questions?
So Milky Way has 100 billion stars in it. If the Milky Way has 100 billion stars in it, and you said that we were going to see 35 billion objects, 20 billion of them being galaxies, why the difference in the number of stars? Is it the same old problem of dust and gas and limiting magnitude, or is it something more?
Yeah, so a huge set of awesome questions. So why do I say we're going to see 17 billion stars, but there's hundreds of billions of stars in the galaxy? So there's a few reasons for that. One, you're absolutely correct. Gas and dust is going to limit the view that we have within the disk of the Milky Way itself. Another reason is even at the extraordinary sensitivity of LSST and how deep LSST is, we won't be able to catalog all of the stars in the galaxy. There's a really large dynamic range in how intrinsically bright stars are. And so, interestingly, the most numerous types of stars, these red, cool stars on the main sequence, are the dimmest types of stars. And so even in areas that are unobscured by gas and dust, we won't be able to see all the way down to the transition between stars and brown dwarfs and planets over the whole volume of the Milky Way. Sir?
So is your plan then to just look at one specific area of the galaxy and then extrapolate that, well, if it's true here, it's going to be true everywhere else? Is that the plan? Because you can't look at everything.
Yeah, no, so that's the great question. Are we going to look at one part of the galaxy or the whole thing? And I should have mentioned this. The main area of the Large Synoptic Survey Telescope, large LSST survey, that's too many surveys, is over half of the sky. Actually, so it will be a huge fraction of the sky that we'll look at. So some instruments and surveys look really deep over a relatively smaller fraction of the sky and then infer what might be present in the rest of the sky. So a reason it's so excellent for studies of the Milky Way is because we see such big differences from direction to direction. There's a stream, there's not a stream, there's galaxies here. Maybe the galaxies aren't uniformly distributed around the Milky Way. And so we can empirically answer some of these questions instead of having to make inferences by having this really wide field view. And so while I'm getting ready to answer the next questions, I also want to reward our two contributing future scientists with some nice LSST-related things that Bob kindly brought. And so we have future scientist here. Could you pass this pin down for her? For having the awesome answer about where the next closest star might be. And we've got a super awesome future scientist in the front who has powerful knowledge of the Oort cloud and the size of the solar system. And there's a cool LSST badge here for you. So thank you both for participating. Okay, so I think somebody over here has the mic. Yes, sir.
Yeah, it's the observation of the galaxy from the southern hemisphere that much better than the northern hemisphere?
So another way of phrasing your question is maybe why is the telescope in Chile instead of instead of being in Tucson? Made in America. So it's a huge consideration, right? What has the best skies for observing? And there's a lot of different considerations that go into it. One is the how great the site is. Is there the infrastructure on the site that could help make the cost more efficient when building a new large facility there? Are there other political considerations, such as, native folks that have a long-standing relationship with the land, and that we need to be very sensitive to issues that could be involved with interest in putting a new observatory there? So it's a complicated set of all these considerations. And Chile, not only was it recently named, what's the official, an official dark sky sanctuary. So the darkness of the skies are excellent. The government has a great relationship with a number of different astronomical institutes and is committed to keeping those skies dark. There's wonderful infrastructure on the number of the mountains there that have both international observatories and observatories that are both managed and co-managed by the United States. And the site, it's fantastic. So after a long consideration process of sites in various countries, the team picked that one in Chile. I wasn't a part of that process.
I've got a peculiar question. It concerns the idea that sometimes in the past there have been astronomical observations that were of differing levels of reliability. In other words, there were some sources that would see something that nobody else could see in that same space. And then there are other, obviously, spaces that everybody agrees on, more or less, indicate various definite objects. Is there any attempt? Obviously, you're going to have an enormous amount of evidence that perhaps will be sifted computer-wise down into a relative degree of certainty. How do you feel about the applying the idea of certainty or probability to the obvious mass of information that you're going to have.
And so more so than ever before, have astronomers been using probabilistic inference techniques to understand what we're seeing and why. To the extent that some folks propose that actually we shouldn't, and maybe this is exactly what you're thinking about, maybe we shouldn't just take the picture and turn it into a list of yeses and nos and numbers with some decimal points, but rather the likelihood that something is a star and the likelihood that something is a galaxy, and sets of likelihoods that could be used to themselves be reconstructed to produce the image. And so people are certainly using inference techniques like this to figure this out. And that is related to your point about, well, how could observations taken maybe with one observatory lead us down to different conclusions than observations taken by another observatory or with varying various qualities. And that's something that's also very important to think about. And one thing that LSST is going to be doing is leveraging things that we have learned from other observatories. For example, there's a mission called Gaia. It's a satellite that's in space right now, measuring the positions of stars to extraordinary precision. We can use that information as sort of a truth. We know exactly where stars are that can help us anchor our own system. Or we can compare observations obtained at LSST and at other wavelengths with other observatories and see if we could combine that information to get a more well-informed understanding of the properties of the individual sources. So those are all discussions that are underway without any set plans for how those analyses will go, but people are thinking about it.
Maybe one last?
Big feet.
Hi there. I really appreciate that you brought up the idea of crowdsourcing and how there's an effort to bring educators into this discussion. So I'm wondering what sort of resources you're going to have available for educators.
That's a great question. So there's, if anyone else is here can speak to that in more detail. So the education and public outreach team is really just getting developed now and looking ahead into what sorts of things we'll be able to provide. So I know that there's very specific conversation about how to provide points of engagement for students in the K through 12 classroom and in the undergraduate classroom, and then also for the interested person who's at home, who's either a well-educated amateur astronomer or who's just an enthusiast. So when I look at the Sloan Digital Sky Survey as a precursor example, I don't know, it sounds like you're an educator yourself. You can go to that website, anyone sitting in this room can go and look at images of any part of the sky. There's different activities and points of engagement, but LSST is going to go a lot farther than that and thinking about exactly how that'll be underway and the method by which the connections and the actual personal touch will be to the classrooms is still under development. And actually, a major theme of this week's meeting and a major theme of what the project is doing over the next year and a half is operations plan. What are the use cases for the K through 12 classrooms? How are we going to accomplish those goals? And how many people will we need to accomplish those goals? And then to present that at the end of 2016 as an overall plan for the project. So it's still all underway, but there's going to be a team of, I think, maybe 8 education and public outreach leaders in astronomy here this week to talk about stuff like that.
This might be a silly question, but
there are no silly questions.
Okay. What caught my attention is you said we perceive the stars blue and red. So the blue was the hot and red was the cold. How is that possible of we perceiving that? So in that color coordination, I don't understand how we can see that the blue would be hot when usually the blue would inquire cold.
Yeah, that's a great question. And it's one of those really common things that students come to the classroom thinking about, because blue, snow, cold. And the one practical illustration that I think of off the top of my head to give is, you ever think of, white hot? When you first stick that poker in your fireplace, it doesn't become white hot first. It glows red and then orange, and as it gets hotter and hotter, it's going over to the bluer side of the rainbow and becomes white. And so physically, what's happening is that blue light in the rainbow is higher energy than red light. And blue light, that higher energy light, is emitted by stars that are hotter on their surface, because of the increased energy.
One last question that I have is the LSST.
No,
I might,
no double dipping.
I'm like that. I just love to get involved with this stuff. Is this telescope going to be hooked up with several other telescopes to make a larger telescope?
The short answer is no. But there will be a smaller telescope to assist with the calibration of this telescope. And as I answered to someone else's question, the observations from this telescope may be coupled with observations from other telescopes, not to increase the effective size of the telescope, but to increase the amount of information we have about each object.
I notice it's a 10-year life for this telescope. Now, if we look at the Hubble and how they want to keep it going and going, I tend to think that in that 10 years, there are going to be as many questions raised as there are answers. And what is the chance of continuing this after the 10 years?
The answer to that question depends on whether people and agencies think that keeping it up is important enough to continue funding it. And a big part of our job, which is going to start before we start that 10 years, is to be thinking ahead, being nimble and agile, thinking about the questions that are raised and the ways in which we can smartly continue to deploy the resources we have and how much resources we would need to continue it on, either with the same sort of instrument on it or with a second generation instrument of the future. So people are certainly already brainstorming and thinking outside the box about questions like that. Oh, do you have a question in the front row? Are you stretching?
Question?
I have this, the first row junior scientists are outstanding, I have to say. Please.
Is there any chances to be used to observe in the future the Andromeda Galaxy or any other galaxies outside the Milky Way domain?
Yeah, so we live in a whole local group and a local volume of galaxies. So the Andromeda Galaxy is located in a place where it can't really easily be observed by this telescope. The Magellanic Clouds, even though they're dwarfy, are actually pretty juicy compared to all the dwarfs that I'm talking about here. So one of the things that's under discussion this week is planning for how well and how wide field and how many times we're going to map the Magellanic Clouds. But the kinds of science that I showed you that we can do by counting up the colors and brightnesses and numbers of stars, we're going to be able to do for a whole host of galaxies outside of the Milky Way and outside of the local group, just depending on what kinds of stars we want to use. So there will be dozens of galaxies that we can map with individual stars like this.
I'll try to frame this right. How do you distinguish between a stellar cluster and a dwarf galaxy? Is there a difference? Have we shifted terminology?
The question you have just asked has been the subject of arguments among scientists for some time. It has been the topic of conferences. I wrote a polemic with a colleague called Galaxy, Defined on this very topic, right? So what is the difference between a star cluster and a galaxy? Because something I didn't go into is these invisible galaxies, many of them actually have fewer stars than a typical star cluster. Okay, so why are we calling them galaxies? So functionally speaking, when I'm thinking about, is this a semantic question? Do I care? Do we need to agonize over what's a star cluster or a galaxy? Okay, is it just semantic? And it is not a semantic question, and the reason it's not is because if I want to understand our theories of how galaxies form, and if I want to understand whether or not observations of our universe are consistent with the predictions of a model which tells us there's a lot of dark matter there, I better know which things are lighting up clumps of dark matter, which stars are lighting up clumps of dark matter, and which stars are not, if I want to be able to test these theories. So one functional difference could be framed as, well, star clusters, they don't live inside a clump of dark matter. When I measure how quickly the stars are moving inside of a star cluster, the amount of mass I need to keep those stars from flying apart is about how much mass I see is contained in the stars themselves. There's not anything missing necessarily, right? What you see is what you get with the star cluster. But when I look at the motions of stars in dwarf galaxies, and I look at how quickly they're moving with respect to each other, well, there's got to be an enormous reservoir of missing mass, otherwise they would fly apart. And with these newly discovered galaxies, the ratio of mass that we can't see to the mass that we can see in stars is in the hundreds or the thousands. And that's just within the little volume within which we can see stars. If those stars themselves are embedded within a great big clump of dark matter that extends physically out very far from the stars, there could be 100,000 times or more dark mass than light mass in these little galaxies. So that's a profound question that we've been thinking about. Thank you.
You got one more question? Last question here. Oh, I should mention at 8:59 p.m., if you look up towards the west, you should be able to see the International Space Station coming over. If you haven't seen the space station before, 8:59 p.m., look up toward the west.
I hear a lot of talk about the missing dark matter. Is there any consideration that maybe something else is wrong with our calculations and there's not as much dark matter, if any, that's actually missing? And we're just, as the gentleman asked earlier, well, you know, is somebody criticizing in a positive way our calculations so that we know we're actually looking for dark matter?
Yeah, so there's been a really interesting shift in the field of this, looking nearby to try to understand the properties of dark matter, especially within about the last 5 years. So at the same time as we're able to use these next generation observations to do a much better job of cataloging galaxies that we thought should have been there but we couldn't see, people have started to really think critically about whether that's actually solving our problem or not. So people aren't just counting up the numbers of galaxies, they're looking at, well, where are the galaxies? How are they distributed? How are they moving? And people are looking very critically about different ways to hold the cold dark matter models feet to the fire. That makes sense. And so there are some, so the modified Newtonian gravity is one model that people spent a lot of time trying to see if that may be a better description of how matter behaves in the universe. And a model like that, if it was to be the case that we have to modify Newton's laws of gravity to really explain what we observe in the universe, it doesn't necessarily mean that there's no dark matter, and so maybe this is something that you were thinking about, but it means that we could potentially get away with a lot less dark matter than there was to begin with. So, you know, just a summer or two ago, there was a conference about using galaxies to investigate the properties of dark matter, and I was on a controversial panel at the end of that, and somebody, after I spoke, said, I might just leave the room, because I was speaking in support of, you know, evidence for dark matter. So it's conversations that are intensely and I think very productively happening, both in the literature and face-to-face by astronomers now. I mean, the cold dark matter is still definitely the prevailing model. There's an enormous body of empirical evidence to support it, but astronomers aren't ones to sit by and say, okay, yeah, we're going to take that and leave it.
Can we please have another hand for Dr. Beth Willman?